My apologies. Indeed. A vision, I suppose, of an integrated information system for project-driven production in construction. You know the rules. Off you go.
Hello, everyone. As mentioned, I'm Manny Pochtar from Oakland University of Technology, and this research envision of an integrated information system for project-driven production in construction is basically conceived by my colleague, Ricardo Antunes, and mostly is developed by him. Let's start the discussion with a very familiar statement that construction appears at the bottom chart of productivity in construction. Among several reasons connected with this low productivity, the lack of cross-functional collaboration between different parts of construction could play a significant role. It originates from interfunctional problems, so we cannot have interconnected components which provide a stable flow of information between different parts of construction. Let's, as usual, make a comparison with manufacturing. In manufacturing, we have supervisory control and data acquisition, SCADA. This system lets us to monitor the operation, collect information, and process information in real time. In this system, we have sensors and maybe cameras which collect information and pass the information to the operators. And so the operators can have this information available on site, even if they are in a remote place. What's the advantage of using such systems? Basically, having access to real-time information helps us to if there is if anything goes wrong, we can take immediate corrective actions. In addition to this advantage, we can input this real-time information to the simulation models, so we can have some prediction about the probable problems we may have further on, so we can have also take some preventive actions. This is an example of a synoptic SCADA screen detail. This is a real case done by my colleague Ricardo. So you can see the operator have access to the information about different parts of operation and the key information about each part of the operation. This information have different pieces, mode of operation, so the operator can see if the operation is automated, or it's manual, or it's a local. Also, the operator will have access to the information about equipment's status. So if it's running, or it has stopped, or it's waiting. If there is any equipment fault, again, the operator will see on the screen, and if the fault is serious, then the system will notify the operator with alarms. And the last piece of information, maybe the most important one, interlock conditions of operations. These are the conditions we need to get the operation running. For example, if you look at the end of the arrow, we have a conveyor belt connected to an electric motor. So we need both the conveyor belt and the motor running to have the operation completed. So the operator will see all the requirements for having this operation done. But as usual, you know better than me, we have significant differences between manufacturing and construction. One of the most important one is in manufacturing, we are dealing with fixed routes. Basically, manufacturing products are moving from machine to machine, or from worker to worker, or a combination of them. So we will have a fixed route of products movement. In the left panel, if you look at, we have conveyor belt which are moving the products and passing it to a ramp. At the end of the road, the products will go to the left or to the right based on their size. And it would be the same for the whole life cycle of production. The only time we may have change in this road is when we are changing the plant, the full plant. But it's not the case in construction. In construction, we are dealing with flexible routes. Basically, we have different types of job which requires different processes. Look at the left side panel. Actually, for example, if we are dealing with concrete, then we have materials in the form of aggregates, water, cement, which the required process is mixing this material. But if we are dealing with steel rebars, it would be cutting, bending, and installments. So we will have different routes. And the other thing is, we have some roads which doesn't even exist when the project starts. If you could run the video, guys. Yeah. So this is a bridge renovation, and we have different stages. It starts from demolition. So at the demolition stage, whatever road we have is related to demolition. But then, when demolition is done, we move to installation, the prefabricated pieces. So we have completely different roads at this stage. So in this study, we try to address or explain how we can address these issues within an integrated framework. This framework is developed based on two pillars, observer effect and Genchi and Motso. The observer effect is referring to a term or a theory in physics. So it defines if the observation act can change the event. For example, if here this theory is saying that if we have an observation, it will alter the event. When it gets to the human science, we can translate it into the observation can change the behavior. So it means that if people get aware of having an observation, they can change their behavior. It can change the system and accordingly the model. So in our framework, we have included a continuous observation and its effect. The second one, Genchi Genbutsu, it refers to a term you know better than me. In Toyota production system, it's saying that get the fact, go and get the fact before making decisions. So basically it means that avoid any middle person for making decision, get the information directly. In order to put into practice these two principles, we need to turn our management office in construction site to a control room, similar to what we had in SCADA. So this control room can monitor this, the system and can steer the production. So if any corrective action is required, they can send the commands to the automated or non-automated part of the construction. If you remember, we talked about a synoptic screen we have in manufacturing. In construction, BIM can play the same role because it provides us with a 3D model and a whole set of information about equipment and workers and schedule. So plus we can connect BIM to the monitoring, which in our framework the monitoring can happen in 3 different stages. First of all, collecting information about the site. Here the data acquisition needs to be mobile, so we may use drones, and as discussed, As discussed, LiDAR, I mean, we have discussion about LiDAR in previous presentation. It's a light detection and ranging, which uses light and reflection to make a 3D presentation of the construction site. When it gets into the indoor information, again, we can use the same system, LiDAR scanning, but using with fixed equipments like sensors and cameras. And we have a bunch of successful experiences in using this LiDAR scanning thing in BIM to identify defection. And finally, we will need to have data from individual components of the construction production. For example, if we have GPS on trucks, or we can install some sensors on the helmet, so we can get information about the individual components. How it can help? Let's say in a case, the site information is showing that we are short of a space for piling material. So the control room would know and send the command to the trucks, preventing them from going to the site and having waste in the form of waiting time. Apart from that, similar to what we discussed about manufacturing, we can use modeling, this data for the modeling and prediction, any problem. And we can take preventive action. But the thing is, processing this much of information just relying on human brain is a hard task. So we need to aid decision makers in this regard. So we may use AR, VR, augmented reality, or virtual reality to let the decision makers to check the outcome of their decisions in a 3D space. And still, it would be hard to process this much of information. So at further stages, we may use machine learning engine. This machine learning engine can observe the pattern in data acquisition and the decision made, and after a while they can imitate this decision making. So this is an example how this system can help us. On the left panel we have just a fixed picture, and you see through the machine learning we can identify the laborers, the number of laborers, and when the first one came into the site, when the last one left, we can check the total duration they've been on site and the energy they've consumed. On the right side, it's about the collecting information about the whole site. So you can see through the machine learning we can identify the truck. Also we can identify different pieces of our project. So through this we can see if that piece of work is completed, and if we have a delay, we can have the same alarm as we had in manufacturing. This may sound a bit futuristic, but the thing is, as you can see on the left, this is a control room used in an oil drilling rig about 10 years ago. So it's possible to use this technology, put these technology together along with some new ones like headsets, and by integrating BIM, LiDAR scanning technology, and AR, VR, we can have a stable flow of information, and we can interconnect different components, and so hopefully we can promote and bring the construction at the chart of productivity to a better place. This research was supported by Magna Corporation, which is a private company. For the continuation of the research, we are still looking for some funding. Thank you very much.